with that, let me just get started, right? So, in the last module, let me just sort of recollect the last discussion we had. We had a transistor that is discharging a capacitor, right? And we said that the gate is going to go instantaneously to VDD and turn on my NMOS transistor, and therefore I can treat this as a resistance R equivalent into CL, right? Of course, now when I do this, where is the source? Yeah? No, of course, that is this thing, but where is the switch that is actually turning it on? Yeah? Correct? So, in this RC model, where should I put my source? So, you agree that when I moved from the transistor model to the R equivalent model, I captured the resistance, but what I have not captured is really this effect. Where is that source? Where do I put it? So, it turns out that this has to be placed like this, CL R equivalent, and I have a source like this, and this source is falling instantaneously. It's like a switch. The moment you turn that switch on, it gets shorted to ground and the capacitor starts discharging. Okay. Of course, this we know very well, right? The alternate is I can also, instead of making the supply fall, I could say I want to charge this, right? Though it will not happen through an NMOS transistor, that will happen through PMOS. We will come to that later. But I could have this equivalent RC model and I say that the source is going to charge, in which case my CL will also charge like this, right? In the earlier case, remember that CL would start at VDD and then discharge exponentially. Okay. So, in summary, if I have an R and a C and I have a unit step function as the source voltage, assuming that this capacitor is discharged at t equal to 0, Vc of 0 minus equal to 0. Then what is the equation for the capacitor voltage with time? Let us say this goes from 0 to VDD. What is it? VDD into 1 minus e power minus t by tau, where tau is equal to R equivalent into C. Okay, and then we said that the delay to actually charge, the gate delay, right, was 50%, so you do 0.693 RC and all that, right. So, delay, right, which is defined as the 50% point, is 0.693 R equivalent into C, right, and okay, let me call this R equivalent. So, now the interesting point, and it turns out that we will see more and more of this model coming into our logic gates and other things. What happens if I have another leg like this? So, this is R2 C2, this is R1 C1, I will call this R1 C1. What will happen if my capacitor is loaded with another RC thing? Okay, the problem becomes even more interesting if I have another wing like this, where I have R3 and then C3. Then I can put one more, C4, R4. Now I could ask you, what is the delay, right, from the input to the any of the destination nodes, right? My destination code node could be node 1, node 2, node 3, node 4. Any of the 4 nodes. If I ask you what is the delay at node 4, given that the input went instantaneously from 0 to VDD, what is the delay for the node 4 to go to VDD by 2, for example, or node 3, node 2. So this is the problem that the Elmore delay model solves. Okay, so so let us consider a simple, not a simple network actually, a reasonably complex network. The same thing that I drew, R2, C2, C1, have R3, C3, R4 and C4. Okay, this is my source node, and I am assuming that the input goes instantaneously from 0 to VDD. That means this is my source, Vs of t is VDD into u of t. This is unit step function, u of t equals 1 for t greater than or equal to 0 and t less than 0. Okay, now let's say that I pick node 2. Okay, let me put down the nodes in a different color, node 1, node 2, node 3 and node 4. Let's say I pick node 2 to be my destination node. Okay, and this is basically my source, by the way. Now I want to calculate the delay from the source to this particular destination. Okay, so I want to calculate tau from source to node 2. Okay, or I will drop the source because it's redundant for all the nodes. I will just call this as tau 2. Okay, so before we do any derivation, let us try to intuitively understand what's going to happen here. Can you tell me what the steady state voltage will be on all the capacitors? At t equal to infinity, what will be the voltage on all the capacitors? Huh? Exactly. So first observation, right? One, limit t tends to infinity of Vck. Okay, because and what is Vck? Vck of t is the voltage across cap Ck. This is equal to VDD. Okay, now do you think the delay to node 2 will depend on C3 or C4? How many yes, how many no? Yes, it will depend on C3. Okay, so majority seems to be, okay, majority tau 2 not dependent on C3 or C4. What about R3 and R4? So the person who said it will depend. Do you think it will depend on R3 or R4? Yes. Okay. Tau 2, most others think it will not depend on R3 or R4. Okay. So this we will try to resolve by the end of this derivation. Okay. So now let's put in some notation. The current through each of these nodes, I am going to call it as I1, I2, I3, I4. Okay. So the current Ik of t, what is it in terms of Vck of t? I'll simplify, I'll drop the Vc, I mean that C I'll drop, I'll call it Vk of t. Okay, just because I don't need this capacitor. In terms of Vk of t, what is it? Ck into d Vk by dt. Okay. Now, it's a reasonable assumption to make that all these nodes are going to charge asymptotically to VDD, but they don't charge at the same rate. Each node is going to charge with its own time constant. Okay. So now we will write down the assumption. Okay, 1. Source is VDD into, U of t, which means it's an instantaneous voltage change. Okay. 2. This is going to be an RC tree. Okay. What does an RC tree mean? It means there are no loops. I don't put R and then take it back. For example, from node 4, I don't put an R and bring it back to the source node or to node 1. There are no loops. It's an RC tree, it just branches out. And the third assumption is all caps are between nodes and ground. That means there is no capacitor in series, right? They are only connected through resistors. This is the necessary thing. Then we are also going to make the fourth assumption, which is very reasonable to a first order, that Vk of t is going to rise asymptotically with its own time constant minus t by tau k. Node 2 will rise with a time constant tau 2, node 4 will rise with a time constant tau 4. Okay. So tau 2 is time constant of node 2, and that's our destination node now. Okay. So can we write KVL between the source node and the destination node? First of all, what is the current that is flowing through R1? Huh? Sorry? Sum of all the currents, right? You apply KCL at node 1, basically all the currents are just going to add there, and therefore this current is I equals summation of Ik. What's the current through R2? I2, right? Therefore, what is Vs minus V2? I can write now Vs of t minus V2 of t is basically a current through R1 into R1, the voltage drop across R1 plus the voltage drop across R2, which is summation IK into R1 plus I2 into R2, right? So now we'll go ahead and substitute all these things that we had. Vs of t is VDD into U of t, right? V2 of t we said is VDD into 1 minus e power minus t by tau 2. T by tau 2, of course, into U of t again, because this starts only at 0, right? This is equal to summation, okay, R1 into summation of IK. And what was IK? Each current, it is just Ck dVk by dt, because the current is through that capacitor by definition. Ck dVk by dt plus R2 into what? C? Okay. So now I am going to bring dt this side. So this VDD vanishes, it just becomes VDD into e power minus t by tau 2 u of t dt. We will put the limits later. R1 into summation Ck dVk plus R2 C2 dV2. Of course, now I am going to integrate both sides. All the Vks are going to go from 0 to VDD in how much time? No. They are going to go from 0 to VDD in how much time? Infinite time. It is an asymptotic thing, right? So this is going from 0 to infinity, 0 to VDD. Okay. So you just integrate this, you will get VDD into tau 2 equals R1 summation Ck into VDD plus R2 C2 into VDD. Okay, which implies tau 2 is R1 into summation Ck, k going from 1 to 4 plus R2 C2. Any questions here? Okay. So let's, yeah. Because to a first order, we want the delay to be accurate. To a second order, yes, the delay may not exactly follow this. But what we want is an first order estimate of the delay for back of the envelope calculations. Right now, if you want the accurate number, you have to do a simulation anyway. Okay, but this turns out that, and it is true, even intuitively, all the capacitors do go like that. Yeah, asymptotically they do go to VDD, right? They may not go exactly in that particular equation, but to a first order, it's more than sufficient for us. Okay. Yeah. So now let's go back to our observations. Okay. 1. It does not depend on R3 or R4. R4. 2. It depends on every single capacitor in the circuit. every cap in the circuit. Okay, so let me redraw that so that we get an intuition for what's happening and why it behaves like this. C1, C3, C4. C2 and R2, R1, R3 and R4. So now you look at what's going to happen. Suppose this node, so the current, you turn on the source, this first will try to charge this capacitor. The potential V1 will go up slightly, but the moment V1 goes up a little bit, current will have to flow and start charging these caps as well, right? So it's very intuitive that it has to depend on every single capacitor, because the moment the source node rises, current gets distributed to all the capacitors. Okay. Now you can also do a limiting case. Suppose I make R3 and R4 0. What will happen to the capacitors C3 and C4? No. What is the effect? What's the net capacitance at node 1 then? Yeah? Yeah. So that is one other check that you can do. In that expression, if I limit R3 and R4 to 0, it becomes a lumped capacitor. In which case, of course, it is R1 into C1 plus C2 plus C3, or C1 plus C3 plus C4, then R2 C2 is there, right? So you can do these checks to intuitively figure out that it has to depend on every single capacitor, right? However, what's interesting is the delay depends only on the resistance that appear in the path from the source to destination. Okay, so what is the path from source to destination? I am starting from the source and going here. This is source, this is destination. So it depends only on the on path resistances. Why is that? Because the current through R1 happens to be the sum of all the currents, right? But R2 is basically just the current through C2, right? So that's why you will see that, no, this is actually to tell you why it depends on all the capacitors. Anyway, let's do that. So if I want to write the delay tau 2, I will write it slightly different now. The right way to use this formula is, because it depends on all the capacitors, first you put down all the capacitors in the circuit. Okay, I am going to, so this is plus, plus, plus. Now I am going to put the resistance values before the C1. Now what should be the coefficient of C1 here? R1 plus R2. You just look at this. If I take so it is just R1 C1. Yeah, correct. No, it is just R1. What about C2? R1 plus R2. So what you do is, you put down all the capacitors, go from the source to that particular node and see which resistances are matching with the destination node that you are considering. Okay, so what did we do? First, for C1, we considered this path. Therefore, only this resistance came into picture. Let me color code it. Therefore, this is R1. Now, I am going to go to node 2, capacitor 2. So, I go from source to node 2 like this. And what are the resistances in the path? R1 plus R2. Now, I am going to go to node C3, right, which I can do in blue. So, I am going to go like this. But my destination is to node 2. So which is the resistance that is common to both? That turns out to be only R1, and therefore this is R1. Similarly for node 4, the same thing will happen. I go all the way like this, and the only resistance that is common is R1 again. Okay? Yeah. 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 So it depends on what you mean by. So I believe you should be able to neglect it. Yes. No, why do you say that? If I limit R3 and R4 to infinity, no, the delay tau 2, if you look at tau 2, doesn't depend on R3 and R4. So even if I limit them to infinity, the number is the same. No, what do you mean by limit? What do you mean by limiting R3 and R4 to infinity? You are going to increase the value to infinity in a sequence, but every number in that sequence is a finite resistance. Correct? That's what you mean by limit. So if that happens, for every finite resistance, the delay is independent of R3 and R4. Therefore, it does depend on C2. What you should check is maybe this first order approximation doesn't work at some very high limits. That you should check through simulation, and that may break. Okay, from the first order approximation we are getting this. That is for maybe there is a reasonable range of resistors and capacitors where this works. That you have to go and double check in simulation where it fails. Okay. So any questions here? Yeah. So that is a very good question. Honestly, I have not been able to get as convincing an answer as I can tell you for capacitors. I am thinking about it. I'll get back to you sometime. Okay. It's got to do with the fact that the current through R3 is just dependent on the capacitor charging. That's all. This is my first order intuition that I have. But I don't have a conclusive answer yet for R3 and R4. Why it does not depend on off-path resistances. Okay, so I'll think about this. Maybe the derivation should give you some hint. So you also think about it. We'll discuss it in the next class, or hopefully I should have an answer by the next class or two. Yeah. Yeah. Correct. True, I know what you're saying. So this is not a very trivial answer. I don't have the right answer yet for this. Okay, I'll think about it. You also think about it, and we'll discuss it maybe in the next class. Okay, intuitively, I don't have the answer yet for that. Okay, through the derivation, it's very evident because they just simply don't appear in the KVL equation that when I go from this thing. The other point to also check is in simulation, if you try this, is it really dependent on R3 and R4 is the question, right? And again, there is a range where that might break. That we have to check. Okay, so the dependence on capacitance is very clear. Resistance is not that clear. Okay, yeah. So let's just maybe do one more example so that we get a feel for this. Okay, or should I do a new circuit? No, I don't have to do a new circuit. Let's do tau 3. Can you tell me what tau 3 should be in this circuit? So what are the steps that I told you? First, you put down all the capacitors, right? Then we'll fill the coefficients of the capacitors. Okay. Yeah. So what should be the coefficient of C1? Yeah. R1. C2. Yeah. Because I am now talking of node 3. The only resistance which comes in the intersection of source to node 2 and source to node 3 is R1. What is it for C3? R1 plus R3. What is it for C4? Yeah? R1 plus R3. Okay? Now, what is tau 4? Again, C1 plus C2 plus C3 plus C4. Yeah? R1 for C2? R1. Yeah, here. Here. This is R1 plus R3 plus R4. Okay? So this you will have to learn to apply very diligently, correctly in various scenarios. Okay?